Hi, my name is Brooke Elander, and today I will be presenting my project on the synthesis of polyethyleneimine-HEMA hydrogels for copper binding applications. My mentor for this project was Dr. Joel Godez. First, I will tell you about how my project came to light. Due to my interest in environmental chemistry, a project was presented to me by local clean water services. This project would assist with cleaning up heavy metals such as copper from water. They had recently noticed an upward trend of copper concentrations from their average of 8 to 9 parts per billion. And so a few years ago, the concentrations had spiked to 17 parts per billion. While those values fall well below the EPA limits of 1,300 parts per billion, Clean Water Services still wanted to begin plans to filter water of the heavy metals in case the EPA were to tell them that they needed a filtration system in place. And so their idea presented to me was using a field of wood chips to make a horizontal filtration system. An image of what this might look like is seen to the side here, where water would be pumped in from one side through to the other. From this idea, many questions arose, such as how did the wood chips remove copper, and was it actually the wood chips that were removing copper, or was it microorganisms or fungi on the wood chips? And so while these questions could have had their own projects, what took me in my project's direction is the question, is the method very effective, or can there be a way that removing copper is made simpler and doesn't require the development of land? And so recalling a seminar earlier in the year given by Dr. Al Nielsen from the University of Washington, he discussed the uses of hydrogels. And so an idea of designing hydrogels specific for copper absorption came about. And hydrogels are 3D networks of hydrophilic, meaning water-loving, polymers that can swell and retain large quantities of water. So the first steps were to see what research had already been done on this idea. And so 2 papers were found and followed, where they both had similar polymers, PEI, and cross-linking agents of epichlorohydrin, or ECH. However, their monomers were different, either soy or cellulose. The reusability of these gels were also tested, and it can be seen here. Over 5 cycles, they had quite good reabsorption values. So while these papers did show gels that were quite viable, I did have questions about them. So from the PEI cellulose literature presented, we were unsure if this cellulose was actually binding to the cross-linking agent or if it just seemingly bound. They didn't produce data on that. As well as in the PEI soy paper, the concerns the gel be using soy as a monomer. And so while it's environmentally friendly, there is potential of hydrogel decomposition over time due to the organic material. And so from those, my project questions arose, and they were, by using a novel cross-linking agent and monomer in conjunction with a PEI, can more robust hydrogels with better copper binding properties be produced than those in the previous literature, as well as what method of synthesis will produce the best hydrogels? So in this research, there were variations that were made. And so one of them was the stoichiometry of the cross-linking agent to the PEI. So 4-to-1 and a 25-to-1 ratio was made, where for every 1 PEI, there were either 4 or 25 cross-linkers. Another was even using a cross-linking agent at all, or omitting that. And the third was seeing if what PEI is dissolved in will affect the gelling process. So the solvents used were either ethanol, water, or chloroform. On the right-hand side, there is an image of PEI with a linear and branched version, where this is the branched version, which I used in my research. This here is hydroxyethyl methacrylate, or HEMA, which acted as the monomer. And this is for VBC, or for vinyl benzyl chloride, which act as my cross-linking agent. And so to form the gels, a step called polymerization, which is where long chain-like molecules form, must occur. And so 3 different methods of polymerization were tested: radical addition, Michael addition, and condensation polymerization. The first one being radical addition. This is a method by which the polymer forms through the successive addition of a free radical building block. Free radicals can be formed by a number of different mechanisms, usually involving separate initiator molecules. Following its generation, the initiating free radical adds non-radical monomer units and thereby grows the polymer chain. So an example of this can be seen here, where the initiator adds to the monomer, the double bond kicks off to a free radical, in which that produced free radical can now bind to the monomer, continuing its process, growing the polymer. In my specific research, the first initiator used was azo-bis-isobutylnitrile, or ABN, where initially ethanol was used to dissolve PEI. Unfortunately, a gel did not form. A reason for this was potentially that oxygen was being bound to the other side of the cross-linking agent, and that should have been a binding to HEMA. So if linking didn't occur between the polymer and the monomer, no gel would form. To prevent this, the materials were added to flasks and purged with nitrogen, meaning that nitrogen was pumped in to force any oxygen out. And so while the use of the initiator ABN in ethanol didn't produce a gel, PEI was rather than dissolved in water. And so this did produce a gel. However, it did require more initiator than anticipated. And so a quick idea of what was occurring in that is the nitrogen here went over to this side, the chloride kicked off, producing the PEI here, are representing the rest of the polymer, and the cross-linking agent was added. Then the initiator can react with the other side of the cross-linking agent, making a free radical, and that free radical can now react with HEMA to produce a new polymer with a free radical open to continue creating a longer chain. And so while this worked, another radical addition method was also attempted to see if it produced better results. So the initiators in this were ammonium persulfate and tetramethylethylene diamine, or TMED. And so similar solvents were used in this, where it was ethanol and water. The ethanol dissolved PEI did not produce hydrogels, where the water form did. It was also tested with PEI dissolved in water and no cross-linking agent added to see if hydrogels could form without having to incorporate the step of adding a cross-linking agent. And so those did form gels. However, the PEI in water solution with cross-linking agent was a more robust gel than those without the cross-linking agent. The second method attempted was the Michael addition polymerization, which is a nucleophilic addition of a nucleophile to a alpha-beta unsaturated carbonyl compound, where it is considered very useful in the formation of carbon-carbon bonds. And so in this image, however, the nucleophiles are either nitrogen or sulfur, and they attack over here, creating this nitrogen carbon bond, or in this case, a sulfur carbon bond. So in my method, the ethylene glycol dimethylacrylate, or EGDMA, was added to PEI. The solvents used were very similar as prior with ethanol. However, instead of water for this one, chloroform was also tested. The PEI solution in ethanol, surprisingly, also did not produce a gel. However, the PEI dissolved in chloroform did. Before it could be tested to see if copper could bind to this part, it needed to be rinsed of all chloroform. So it was rinsed with water for 24 hours, and then it was rinsed with dichloroethane for 24 more hours. Unfortunately, once rinsed with DCE, the gel ended up dissolving and rather forming a hard white solid instead. So that method could not be used. The last form of polymerization is condensation polymerization. This occurs with a bond forming between the carbon and nitrogen and a small molecule being produced or released as a byproduct, in this case, water. So for mine, this synthesis method is much like a nylon one, and if successful, it would produce long thread-like polymers. PEI dissolved in water solution was used for this method, and the adiopolychloride was added to it. Tongs were then inserted directly into the flask, and a thin and long thread-like structure should have been removed from the flask. However, what was actually produced was more of a clumpy, stretchy goo-like substance. And so while this didn't produce the best gel, the method could potentially work and should be further explored, because if optimized, it can produce a hydrogel thread that has many application benefits. And so this can be seen here, where the nitrogen carbon bond forms and the byproduct is HCl. So the results overall is that the best methods that worked were radical addition using PEI with the crosslinker in water and PEI without the crosslinker in water. The more robust gels formed from the PEI crosslinking solution. However, when determining visual binding of copper, PEI sans crosslinker was used due to the ability to omit a step that the other PEI solution required. And so characterization of the gels was limited due to time. And so a visual test was performed by making a copper solution that ranged in concentration from 100 parts per billion to 10,000 parts per million. And so visual binding means that blue color appears. And so one of the great things about copper is it's like a light blue solution, but when it interacts with PEI, it turns a quite vibrant blue color, which can be seen in these images. And so the lowest visual binding occurred at 100 ppm. This can be seen where there is a faint blue line here, and none rest in the rest of the gels. So this, once again, if more time had been allowed, then optics would be used to determine if copper had actually bound to those gels and it just was not visible to the naked eye. So further work, there is much to do since this is a brand new idea that I've been working with. Further developing the methods to see if the synthesis can be made simpler and if the gels formed can be more robust. Once that is determined, seeing if the copper's absorption drops after washing off and then replacing into a copper saturated solution. And then lastly, developing into a commercial product, such as weaving, as mentioned, like the thread-like structures from the condensation polymerization, or 3D printing of gels to create meshes. Lastly, I would like to acknowledge Joel Godez, Julian, or Jules, the chemistry department faculty, and my parents. Every person is very vital in what I've been able to produce today. And so I eagerly await your live questions.